And you can thank him again in a minute, because the next talk is also given by Pascal. This time with different co-authors. This is continuing the quest for polynomial time heuristics in PDDL, input size, tractable cases for lifted HED by Pascal, Alvaro, Daniel, and Jörg.
Thanks again for the introduction. I again have a very funny, simplistic task for you, but a different one. It's inspired by the child snack domain, where you want to have a waiter who creates burgers for some person according to their desires. And basically how we would model this in PDDL is that we would create a make burger action that creates some burger, and then we want to serve it according to the preferences. So the concrete encoding would look like this, that we have an action with parameters for the bun, the patty, and the rest, and then we assume that something is in the kitchen and we can create a burger, but it's no longer in the kitchen, and then in order to serve it, we want to fulfill these preferences, but obviously don't have the burger anymore. We describe this with first-order logic, so kind of in a PDDL setting, and so I have predicates for in kitchen likes burger served and the different kind of objects that are in our kitchen. And the important part is that we really just use these action schemas but don't enumerate everything. So the problem with this is kind of, what if you have a really large burger? Like, then the arity really blows up and we wouldn't be able to use the normal classical planner setup anymore, which grounds your representation first, just by enumerating all these different kinds of burgers you could create. And this is a topic that has been re-explored over the last years. Basically, like, the foundation was built by the guys in Basel, by Augusto Correa, which was able to derive a lifted successor generation. And now that we have a lifted successor generation that scales up somehow, the question is, how can we derive heuristics for it? And I tried to approach things from a somewhat theoretical perspective, and if you operate under the assumption that HED is helpful to solve a planning task, you could ask, how helpful is it within this framework? Can we actually guarantee for some planning tasks that it's tractable to compute it, whereas it would not be tractable to ground the task and then solve it? To understand what HED is, we typically in Saarland explain this with a table like that, where we assign a value to each of the atoms. Initially, everything that is in the initial state gets value 0, and then we progress through the table by adding up the preconditions of an action and assigning the sum of the current table values to the next fact, and then we do like a round-robin iteration to get to all these values. So what previous work has shown is basically how to get rid of the bottleneck if you have too many parameters in your actions. So kind of a more efficient way to get through the arrows, but not to downsize the table. So this table would still come with our exponential amount of facts by representing the burger atoms, and we wouldn't be able to compute HED this way. Yeah, that's exactly illustrated here. So what we try to analyze is this a general bottleneck? Is our algorithm just stupid? And we were looking at this through the lens of complexity theory. So it's really easy to show just by the delete relax plan existence in a lifted setting being x time complete, to show that HED, because it can detect delete relaxed reachability, is also x time complete. And the thing I've just shown you basically tells us that if we are able to bound predicate arity, and we somehow can assume that our queries, so the preconditions, are easy to evaluate, this leads us to a polynomial time procedure. But we are somehow not able to come up with a solution for this problem of having these exponentially many facts. And this is where we try to chime in to come up with an algorithm which can compute HED, even if the amount of facts we would ground naively is exponential. Okay. So the concrete property we specified is that if the h@ value is bounded per Go effect, we are able to derive a polynomial time procedure. And I think if you read this for the first time, you think like, why would you care if the heuristic value is bounded? But this bounded per Go effect really makes a big difference, especially like in the task we like to illustrate, because essentially a very big task does not necessarily mean that we have one thing that takes very many consecutive steps. It could be that there are really many small tasks that add up to a huge heuristic value. And one such thing is the child snack example I've shown you, or any planning guy loves block split. So imagine that you just want to stack a few very small towers of blocks. Then it's the same thing. Like per sub-goal, you want to achieve the h@ value is very small. And in this case, our computation will be more efficient. So I say it will be more efficient a lot, but where does this efficiency come from? Essentially, when I was saying that this forward approach by filling out the table is efficient, what we use is query evaluation techniques from databases that try to enumerate in some way what output is produced. And the output would be the achieved facts. And we said that all these achieved facts are somehow a problem. And we can get rid of the problem by just asking, hey, I don't want to know if I can which facts I can reach, but rather, can I reach a fact? So if we would just insist on, can we fulfill this condition instead of what are all the things that fulfill it, we can evaluate this far more efficiently. Essentially because you can evaluate this by replacing the parameters in this join tree with objects and then getting rid of some again. And so I think from what I read in the reviews, there was one big misconception because initially we always said we have a lifted backward computation of h@, which we will get to in a second. But the highlight here really is that we have a lifted computation of h@. So like the backward thing will just be a necessity to make it work with just answering certain conditions. What we do is we basically do like the most basic thing out there. We just do like a lifted regression. We start at the goal, and then we look at the precondition of an action and we replace it according to the parameter that's fixed in our goal. And we leave all other parameters as variables, so like without the object replaced. And then we can do the same thing over and over again and check these queries over our current state. And I just claimed that we can somehow do this efficiently from existing results in database theory. And the nice thing here is that if you sum up the sum of actions that leads to the shortest path in this regression graph, that leads to a fulfilled query, it will be h@. I don't think that's like very easy to observe, but I will try my best to give somehow of an intuition of that. So essentially what the original equation would look like is the very left. So we just sum up over the fact values. If instead of writing this equation as a sum over all things at the same time, we just pick one fact and leave the other sum as is, then that's the same equation. So we kind of, by fixing one atom to replace, we kind of rewrite the sum so that we just use the minimal achiever for one of the facts. And then the next step to keep it lifted is essentially just using this property that the lifted schematic way of exploring things and the grounded way are the same thing. Okay. So why this is true, and I told you you could use this exploration, we actually wanted to test this in practice. So like in this way, you could prove that you have a polynomial time procedure for h@ in cases where you cannot ground to a polynomial task size. But we also wanted to somehow make this empirically scale. And there are some obvious caveats with this technique. So if you do simple regression, already adding 2 goals would, so adding n goals would make it scale exponentially. Essentially, we would go over all these iterations, but there are some simple tricks to make this work better. What we can do is, first of all, look at the parameter connections in our query. So if the query can be split into subqueries which don't have connected parameters, we can handle them on their own and just sum up the values. That's the first optimization. The second one is we can look whether one subquery is unsatisfied, and if we can find a subquery that's unsatisfied, we can only explore the facts for this subquery. So kind of I try to illustrate this on the right here, that we really just replace served C1 if we know that served C1 is unsatisfied. Because like the intuition behind this is that any other query will not have an effect on replacing this, and we have to replace it anyway at some point. Okay, so what does this look like on benchmarks? Essentially, what we are looking at here are these new kind of benchmarks which are designed to challenge a grounder. So like most classical planners will at least be very challenged to ground these kind of tasks, which is why we are looking at it, why we are trying to face them with a lifted successor generation. And if you look at the backward approach, then there's basically one domain where it really shines. So in the logistics domain, it's able to solve a lot more than before, and it is able to gain some slight advantage with our optimizations in Bloxworth and Scheidznack. But in general, like the forward exploration is still better. But the thing here is really that if you look at the theory behind it, we were not trying to find a competitor for that forward exploration. Rather, what we were trying to do is find a computation which does better in cases where the forward exploration cannot be good. And I feel like, in a sense, we achieved this here because the combination of all is really the best, and you can really see that the behavior is quite different. I think you can even see this better in the scatter plot. So here we look at the evaluations per second in a search and the search time in all these domains between the forward and the backward exploration. And here we can get a few more dots because apparently in some of these domains, HED is actually not very well informed and so does not increase coverage as much. But we can see that at least these computational properties we were talking about hold, that there are a lot of domains where the behavior of both approaches is very different and split by the diagonal. And so it would motivate to extend this approach to more advanced techniques like FF, or then integrating the FF into a llama. Okay. So thank you for your attention.
Thank you. Any questions?
Nice talk. I just had a question on, have you tried comparing the lifted computations to the grounded ones? As in, have you tried this approach on the standard IPC benchmarks that we try? So this, I believe this is all hard to ground instances, right? And so what's your perspective? Like, is there a gap in the quality of heuristics, or if you have tried on any of that?
So like it's quite a long time ago that I finished this. It might be that I tested it, but at least I don't recall. I agree that it's interesting, but I would guess that I tested it and the results were just not as interesting yet. So maybe just to clarify, the general field of this like lifted heuristic search at the moment is typically that we get very close to the performance of grounded planners, but not quite there. But in the case where you're not able to ground the task, you can suddenly solve the task instead of not being able.
My question was more in the sense of, is there any benefit of using grounded heuristic, or we can just use lifted heuristics for tasks? So that's what I'm trying to understand.
Yeah, so if you can ground the task currently, it's the case that the grounded planners also perform better. It's really the case. If you cannot ground it, then you need some other tool.
Okay, so might be a little bit of a stupid question, but so I think in the earlier slides there somewhere you had that there is already a polynomial procedure for lifted H max. Or did I get that wrong?
So what I was trying to say is
no, it was like a little bit earlier. So there. No, like no. Well, somewhere you were citing a previous result that H max is also lifted. H max is polynomial, right?
It's okay. So maybe I was bad at explaining this. So there was an existing algorithm before writing this by Augusto in order to compute H max and H add, and implicitly, without them proving it, this algorithm had certain properties, so that if you look at the right task fragments, it's polynomial. But they actually didn't identify it. I just wanted to know, like, when is this thing good? And we added the complexity result on top. And this is the one that if predicate arity is bounded and you look at this asterisk, that you can evaluate queries efficiently, then it's in polynomial time.
Okay. I'm not sure still if I understand this, but so are these two, because for, let's say for H max, I mean the value is always bounded, right, in some way by something. But are these two different proofs of tractability for the same procedure?
No,
or are they a new procedure
so like
with a different proof of tractability?
Before the question, the bounded predicate arity and efficient query evaluation basically correspond to the procedure of Augusto. And then alternatively, if you don't bound predicate arity, because this was the whole point of finding some kind of fragment where we can even compute H add if predicate arity is unbounded, then we look at if H add is unbounded. And there it's a bit harder to define the queries you're able to evaluate queries efficiently, because it basically depends on the type of queries you encounter during the whole search exploration.
Right.
So maybe to put it differently, like the top half is with respect to this procedure. The bottom half is with respect to the new one of us.
So okay. So essentially two different ways of computing H add, but both of them would apply to H max as well, and they have different conditions for when they are, different bounds for tractability.
So it's for H add. You could also make it H max, but the regression thing is a bit more tricky with H max.
So would it make sense in some of these domains to do a partial grounding? So for arguments of the actions that don't have a very big domain size, to do a partial grounding of that, and then do something together.
I'm not sure. So the thing is, I tried this before, and kind of intuitively I would agree there must be like some room in between where you create some kind of partial grounding. The problem is that we always operate within the scope of the IPC instances, and at least there it's really hard to find this middle ground, because most of the benchmarks are designed to be groundable. But yeah, in general, there probably is some kind of option to do some kind of partial grounding. And did I misunderstand the question? Because you look really confused.
It's just because it's late in the conference.
Okay.
Any more questions? No? Then thank you again.